If you have successfully extracted the root file system from the firmware file of your device, and if you want to understand what your device does after booting, and if there is an easy way to log in as root, this is the video for you. We will talk about analyzing startup scripts of an IoT device to understand what the device does, if there is any possibility to log in as root, and to identify some interesting binary executables to reverse engineer to hack the device. I am Valerio Di Giampietro. I am an electronic engineer with a background in digital electronics and information technology infrastructures. I would like to be your friendly Italian hacker neighbor, willing to share with you tools and techniques for hardware hacking that I learned by myself hacking many devices. If you have not done yet, please subscribe and click the notification bell below to be notified when new episodes will be released. And now, let's start! This is the 6th episode of the series Hardware Hacking Tutorial. In this complete series, we will talk about the hacking process based on information gathering from our device, building an emulation environment where to run interesting binaries, discovering how the device works, and then hack the device and modify its firmware. This episode is about analyzing the startup scripts of our device. This is the first step in discovering how the device works, and it is a preliminary step to do before building an emulation environment. We assume that our device has a Linux or Unix-like operating system. This is true for the overwhelming majority of devices. When some examples are needed, we will analyze the startup scripts of our sample Gemtech router, link in the description below. We will start from the beginning, that means from the boot of the operating system. We will look at what type of init process we have. We will analyze the init configuration file and related startup scripts. We will identify the most interesting binaries that manage our device. We will identify the login process. We will look if there is the possibility to access the device as a root. We will use common Linux commands to do this analysis, like a text editor, the grep command to search inside the file or multiple files, the find command to list files that interest us, the xargs command often piped after the output of the find command and coupled to the grep command, the strings command to display strings embedded in binary and executable files. The large majority of IoT devices run some form of Linux or Unix-like operating system, so they have a Unix-style init process. Init is the first process started by a Linux or by a Unix-like operating system. There are many different variants of the init process, but many of them belong to a family of similar processes that read what to do next from the same configuration files. We have the BSD-style init process. BSD stands for Berkeley Standard Distribution, and it was a popular Unix distribution in universities and other academic institutions. Today, the most popular BSD-style Unix is the FreeBSD. Originally, BSD init started executing the scripts rc and rc.local in the /h folder. More recent versions of BSD init read the configuration file rc.conf and executes related startup scripts located in the hrc.d and corresponding folder in the user local folder. But by far and large, the majority of embedded Linux Unix systems use the System 5 style init. System 5 was a popular commercial Unix distribution originally developed by AT&T. The most popular init process of this category in the embedded world is the BusyBox init. BusyBox is very popular in embedded devices because it is optimized to save EEPROM and memory space. In a very small binary of less than 1 MB, it implements, with some minor limitations, a lot of Linux commands like the init process, the shell, the ls command, the grep command, and many others. This family of init processes read the configuration file from the file h-init-tab and, according to this file, starts related processes and scripts usually located in the init.d folder. Recent Linux servers and desktops use the systemd init process. Systemd's initialization instructions for each daemon are recorded in a declarative configuration file rather than in a shell script. It is a much more sophisticated, powerful, and complex startup process aimed mainly at server and desktop environments. I have never seen yet systemd in an embedded device, where usually simplicity and low memory, low disk footprint are preferred. All this discussion about the Unix Linux init process means that one of the first information that we need is what kind of init process we have. This is needed to understand what commands, daemons, and processes our IoT device executes after booting. We can usually get this information in multiple ways. It is usually printed on the serial console during boot. For example, in our Gemtek sample router, during boot we can see that on the serial console it is printed the string init started, BusyBox and is version. On another Netgear router, during boot we can see that on the serial console it is printed a similar string with another version of BusyBox. We can also analyze the root file system, where the init executable is usually located on the sbin or bin folder, and, for example, in the root file system of our Gemtek router that we extracted in the previous episode, we can see that init is a link to BusyBox. If we use the strings command and look at what is inside this binary, eventually piping the output to some grep commands, like grep/h, we can successfully identify what type of init we have. In the BusyBox case, we can see that the string h-init-tab is included in this binary. As another example, a bit unrelated, if we do the same on our Ubuntu Box 18.04 version, we can see that init is a link to systemd. If we use the same strings and grep command used with the BusyBox, we can see that there are no references to init-tab, but there are multiple references to configuration files located in the systemd configuration folder. In our Gemtek sample router, we have seen that our init process is a BusyBox that read its configuration from the init-tab file, so we start looking at this file. We can see that BusyBox doesn't support run levels. Run levels are usually supported on server and desktop systems, and in some cases also in embedded devices. Run levels are a way to specify what kind of startup scripts to run based on the defined run level. It is possible to configure the default run level, and it is possible to change the run level dynamically restarting the system. Usually, the run level 1 is the single user mode, where almost no daemon is running and the user is presented directly with the root shell without need to enter a password to log in. Run level 3 is a text-based multi-user mode with a text-based login prompt and no graphical user interface. Run level 5 is the graphical-based multi-user mode with the graphical login screen. But in our case, we don't have run levels. This router we always execute the same startup scripts. In our case, we can see what init process will execute on startup. It initially set the system date to the date of the init executable. Later, in other startup scripts, it will use the network time protocol to set the correct date and time, because this device doesn't have a real-time clock. Then it mounts the Proch pseudo file system used by Linux as a file interface to many kernel-related information. Then it remounts the root file system in read-write mode. It is the squashfs file system loaded in RAM. Then it creates folders that will be used as the mount point for special file systems. Then it mounts everything specified in the fstab file. Then it assigns to the device the hostname specified in the hostname file. Then it configures kernel parameters from the default file sysctl.conf. And finally, it starts the startup script RCS. The TTY S0 line specify to spawn the getty command to start a login prompt on the serial console at 115,200 bits per second, emulating a VT100 terminal. Respawn means that if the getty process dies or terminates normally, it is restarted. The other lines specify what to do when Ctrl-Alt-Del are pressed and what to do at the shutdown of the system. There are two items that we want to check more in detail. One is Getty. If we look at the Getty manual page, we can see that it opens a TTY terminal, prompts for a login name, and then starts the bin login command to prompt for a password on the terminal and to start an interactive shell. But we have seen in the previous episode that on boot we received the login prompt, but instead of receiving a password prompt, we received a challenge code. This means that we don't have the usually Linux bin login. We can check on the extracted file system and we can confirm that bin login doesn't seem to be the usual bin login, but it is a link to a custom login executable called shellout. This is a binary file that it is a candidate to be reverse engineered later in one of the next episodes, after we have built an emulation environment. The second item that we want to check is the RCS script, that it is the startup script for our device. It executes every script starting with an uppercase S located in the init.d folder, passing it the start parameter. Scripts ending with .sh are sourced in the same RCS script process, without forking another subprocess. This is done for efficiency reasons to save memory and processing power. Scripts not ending in .sh are executed as normal subprocesses. If we look at these scripts, we can see that many of them seem to be pretty standard Linux stuff. It would be useful anyway to look inside them to better understand what they do, but in this video we will look only at the two custom scripts that are device-specific. The first device-specific script is s15 createaccount.sh. We can see that in the root file system that we have extracted from the EEPROM in the last episode, the password, group and shadow files are links to corresponding files in the read-write UBFS file system mounted under the folder mnt/jffs2. Anyway, in the h folder we have the related default files. Without going into much detail, we can see that this script sources the build root config file. It would be interesting to see what variables are defined there, but for now we will move forward. Then, if the UBFS file system doesn't have the password, group and shadow files, they are created copying the default files stored in the SquashFS root file system. Some more processing is done based on the content of the build.root config file where some variables are defined. This processing is done if the UBFS has not yet these files. This probably happens only on the first boot of the device or when the device is factory reset. We can take a look at the default password and shadow files, which are the initial password and shadow files. We can see that root is the standard shell and that is a regular hashed password in the default shadow file. We could immediately try to crack this password with the hashcat, but following the easiest path first principle, we can try to search this hash directly on Google. Now I am not able to find anything meaningful, but a few months ago, when I tried, I was able to find the password in a forum of hashcat users where they were exchanging hashes and they recovered the passwords. So I was able to recover the password without running hashcat. The password corresponding to this hash is 5/4JP6. It is only 6 chars long, so it is quite easy to find it with hashcat using a brute force attack. Link to hashcat in the description below. The problem is that if we try to log in on the serial console, we don't receive a password prompt, but we receive a challenge code. And if we put this password as challenge code, we fail to log in. The other device-specific startup script is s99gemtech.sh. Analyzing this file, we can spot very interesting things. We can see that if the environment variable factory has a value greater than 1, a special IP address is assigned to this device. Again, if the variable factory is defined and has a value greater than 1, the device enters in factory mode and executes a telnetd daemon executing a root shell. This means that if the variable factory has a value greater than 1, then we can connect to this router with the root shell without entering a password. Then some commands is executed to inform someone on the same factory subnet that this router is alive. Probably this facility is used during production to have the router to enter in factory mode, announce that it is alive to some test equipment, and have the test equipment connect back to it to execute some additional configurations or some additional tests. Then, if factory is equal to 2, a fw settemp factory command is executed, probably to reset the factory value so that at the next reboot the router will not enter the factory mode again, but will enter the normal user mode. This means that if we want to leave the router in factory mode across reboots, we have to set this factory variable to a value higher than 2, for example 3. When we want to return the router to the user mode, we can unset this variable manually with the same fw settemp command as this script does. By the way, I found that in many devices there is a factory mode, and it is much easier to hack into a device when it is in this mode. This means that it is usually convenient to search the string factory mode in the root file system of our device to see how, if possible, how to put it in this mode. The problem for us now is where this lowercase factory environment variable is set. Not in this file, because it is used for the first time in this assignment line. Not in the build.root config script sourced at the beginning of this file, because there are no factory variables in this file. we could try to search where the string factory is located in the entire file system using the following shown command. Find space dot is used to print every file starting from the current folder, that it is the root folder of the squashfs root file system. Minus type F is to limit the printed objects to only normal files, excluding special device files, links and folders. Xargs is a nice command that read from the standard input and passes as parameter what it read to the following command. In this case, grep-l factory will be executed for all the files printed by the find command. We limited this list to only normal files to not receive errors on folder or device names. The -l option is to list only the name of the matched files and not the matching lines. To be honest, this command will correctly function only if we have file names that don't have a blank or a shared special character in his name. Otherwise, to be safe, we have to use a slightly different syntax. In this case, in the find command, we use print0 instead of print. This means that find will list every files separated by a null char instead of a blank or end-of-line char. In the xargs command, we use the -0 parameter to tell xargs that input items are terminated by null character instead of by white space, and quotes and backslash are not special. Every character is taken literally. In either case, we find nothing meaningful. We have to look at other files implicitly sourced by the S99 gemtech.sh file. One of these files is hprofile. We can see that there is a command to export all U-boot variables in a temporary file, and then these variables are imported after cleanup as shell variables. This means that the factory variable is set in the U-boot bootloader environment. This probably means that if we set this variable using the U-boot command line interface, we can access the device as root. We will try soon. At the end of the S99 gemtech.sh, we have two commands that probably are the two applications that manage the router. So we will do some analysis on these two executables later. Now we try to log in as root, setting the U-boot factory environment variable. We connect our Linux box to the UART serial interface. For more details on how to do this connection, you can look at the second episode of this series, link in the description below. We connect the Ethernet cable between one of the LAN interface of the router and our Linux box. We launch our terminal emulator, power on the device, wait for the bootloader menu, press 4 to select the command line interface, and we have the U-boot command line interface prompt. We type help for the list of commands, then help printf, and then printf factory to see the current value of the factory environment variable, but we see that it is not defined yet. So we type help setemp to see the setemp syntax, then we enter the setemp factory tree to set to tree the value of the factory variable. We confirm that the value has been assigned with the printf command. We now save the environment in the EEPROM permanent storage with the saveenv command. We can type reset or power down, power up the device to reboot the router. Now, after reboot, the router should be in factory mode with IP address 192.168.15.1. We have connected an Ethernet cable between our laptop and one of the LAN ports of the router. We assign an IP address on the same subnet to our Linux box. We can check that our router responds to ping, and we can execute the telnet command, and boom, we are root in the device without needing a password. We can verify that we are in our device with the uname-a command that tells us that the name of the device is build-root and that it is a MIPS device. With the cat/proc/CPU info, we can print info about his CPU and number of cores. We can also do a cat/h/os release to print some information on this Linux version. Why they have spent time in rewriting the login executable requiring a challenge code to prevent login from the UART interface when it is so easy to login as root in factory mode remains a mystery. We can now return to analyze the last startup script s99gemtech.sh. We have seen that the last two processes that are executed are Prochmon and MSG Center. They seem to be the two main custom processes of the router. We can use the strings command to have an idea of what these two executables do. We can see that Prochmon probably executes a lot of commands. Some of them are shown here. It executes a lot of kill command, but also starts some daemons. So it seems a process that monitors some other processes and restart them if needed. The MSG Center executable seems to execute a lot of basic commands to configure the router, like ifconfig, iplink, insmod to insert modules into the kernel. It has a lot of strings embedded inside, and it requires a lot of time to analyze it. But one of the interesting commands embedded inside this executable is the assistant command. It seems a command that can generate some passwords, like XVoIP password, and we don't know exactly their purpose, but also probably the Wi-Fi password. Especially the last line seems the command to generate the Wi-Fi default password of the router. The $serial could be the router serial number. Then we have a string. Then the cat command extracts the first 8 chars of the output, and the tr command will convert everything to lowercase. If we look at the label of our router, we can see that the password is a string of 8 lowercase chars, so it is compatible with the above cat and tr commands. We have the serial number. The unknown string in the assistant command could be the last 6 chars of the SSID, that, by the way, are the last 6 chars of the LAN MAC address. We can connect to our router that it is still in factory mode and it is still connected to our Linux box, and we can try to see if our hypothesis is correct. So we type the assistant command, we put the mysterious string in the -p option, probably it is a sort of password to prevent the use of this command to the few people that don't know how to use the strings command. Then we put the -w Wi-Fi option, and then we pass with the -h parameter the serial number of the router, and at the end we put the last 6 chars of the SSID in the -s parameter. We execute the command without piping it to the cat and tr command, and bingo, we are right. This is exactly our password. But in a mixed case, if we execute exactly the same command inside the MSG Center, with the cat and the tr command, we get exactly the default password of our router. This means that we have found the binary file to generate the default password of our router and probably of every router of this type. This is the binary file that in a future episode we will reverse engineer in our emulation environment to understand how this password is generated. Once we have reverse engineered the algorithm, we know that the -s string is known because it is the last 6 char of the SSID. The serial number can be generated joining together the string GMK, the year, month and day of production, plus a 6-digit sequential number. If we lost the label of our router, we know the SSID because it's broadcasted, but we don't know its serial number. We can easily generate millions of serial numbers, for example for the last 10 years of router production, and then we can capture an handshake between a client station and this router, and using Hashcat we can recover the default password in few minutes. We will do this in one of the next episodes after having built an emulation environment where to run and reverse engineer this binary. The other binary that we will reverse engineer in a future episode is shellout, the script responsible for the login prompt with the challenge code. In this episode, we have seen how to analyze the root file system to understand how our device works, since when it is switched on and starts executing the init process and the startup scripts. We have also seen how analyzing the startup scripts and using simple Linux commands like find and strings, we can identify easy to exploit vulnerabilities and interesting binaries to analyze and reverse engineer later. In the next episode we will talk about how to build an emulation environment that is debugging friendly and reverse engineering friendly, where to run and reverse engineer these interesting binaries. If you have found this video interesting, please subscribe, help this channel grow, share the video with friends interested in hardware hacking. Please click the subscribe button and the notification bell to be notified when new episodes will be released, and don't forget to click the thumbs up icon. Please let me know in the comment below if you have found this episode easy to follow, or if you have found that my bad English is a big obstacle in understanding the content. Anyway, you can enable closed caption or subtitles where you will find everything I say in plain English. My script abilities should be better than my verbal abilities. Please give me feedback, writing comments below. Let me know if you have suggestions to improve this channel, or if you have enjoyed or not this video. Every comment, but positive and negative, is welcome. Thank you for watching. See you again on this channel.